Hello again. Let's learn about graphical solutions. So we just learned how to make a bunch of different graphs and we don't know how to use them yet. So we can look at them and get some information just visually. But another thing that you can do is actually use them to solve problems. And that's what graphical solutions refers to, is using the graphs to come up with solutions. So let's take an example about, say, like an electric bill. You could have this graph, something like this, of light bulb power usage. And so you collect some data on the power use over time. So say it's a 50-watt bulb. When you turn it on, it consumes 50 watts. When you turn it off, it consumes 0 watts because there's no energy going. And so that looks something like this. It's flicked on, it's flicked off, it's on again, it's off again. And you want to go from that power that you measured to energy, because what you actually would get charged for is the energy that you use. And so what we know is that energy is equal to power times time if we multiply them. And that product is actually the same thing as the area on the graph of power over time. So to multiply power times time, we could actually just look at the area of this rectangle inside and get how much energy was consumed during that time and how much energy was consumed during that time. So to get the total energy here, we just add up the area of these two rectangles, which is going to be, they're both at 50 watts. So 50 times 2 for that first one is 2 seconds, plus 50 times, looks like it's 3 seconds long. And then we need an equals at the start. That's why it's mad at me. Equals, and there we go, 250 joules of energy was consumed by this 50-watt bulb. Okay, and that is not all. We can go the other direction too. So let's say that we had measured energy use of a light bulb and we wanted to know about power. So in this case, we'll use the inverse of that relationship. Power is energy divided by time. And on a graph, this looks like the slope. So this is the same like information as up here, but measuring energy use instead of power. And so if we look at the change in energy and the change in time, then we can get the power. So if we look, say, at this upper chunk here where the triangle is, the change in time is 3 seconds. It's 4 to 7 seconds. So I could also just say 7 minus 4. And the change in energy is going to be, it's 250 at the end, it's 100 at the start. So that's just going to be 150. And then to get the power, I look at this and I say change in energy over change in time. Well, that's going to be equal to this energy one divided by this time one. And there's my 50 watts of power, which is the same as the slope of this line. So if you remember like a linear equation of y equals mx plus b from like an algebra class, that m value is, in this case, the power. And that's often like a parameter about something in your system. Okay, moving along. What else can we do with this information? This is a similar idea where we look at slope and the relationship between two variables. But now we've measured voltage and current, and we want to know about resistance. So in an electrical circuit, voltage is equal to the voltage drop across a component is equal to the current running through it times its resistance. So we can rearrange that to say that the resistance, a sort of inherent parameter to an electrical component, is found by looking at the voltage drop across it, which you can measure, divided by the current through it, which you can also measure. And so we can just kind of pick a point off this graph, say this one right here is at 40 volts and 0.8 amps. And I can plug that into my equation since it's linear, 40 volts divided by 0.8. Again, I need equals 50 ohms. So this happens to be a 50 ohm resistor. And that's like a really important physical property. In real life, you've got wires with resistances all over the place in how electricity works and how your home gets wiring and how like businesses do things. And so this is a really important. Okay, welcome back. So here's another example where we're looking at sort of a linear relationship between variables and trying to figure out a property of like a physical thing. And so in this case, instead of an electrical circuit, we're looking at a steel bar, and we're saying the relationship between the stress on the bar, or the like force that you apply to it relative to its area, is related to the strain, which is like how much it sort of stretches or compresses um, linearly relative to its length. And that's what stress and strain are. You learn about this in a later class with me. But the modulus of elasticity is a sort of inherent material property that relates them. And so you could think of this as like the difference, one of the differences between like rubber and steel is that steel has a much higher modulus of elasticity, meaning you need to give it a much higher stress or force in order to see it strain, which is to like move, change its length. So you maybe have never even visibly seen a steel bar change its length at all, whereas a rubber band you can stretch really easily. It doesn't take a lot of stress. So you could find the actual number here by looking at this and similarly picking off a stress value of 0.08 gigapascals here and a strain value of 0.0004 meters per meter. And so that's going to be 0.08 divided by 0.0004. 200 gigapascals is the modulus elasticity for steel. That's very high. Well, if you take a materials course with me, you can learn more about this. But like rubber would be much, much lower. It might not even be in gigapascals at all. So many orders of magnitude lower. Okay, finally, our last example is kind of combining both of these concepts of area and slope. So if we had, say, a car race, and we've got two cars that are driving, and we have measured their velocity over time. So we know velocity at every second point in time. And what we want to figure out is a few different things about how far they've gone, like their distance, and how quickly they've accelerated their acceleration. And so if we know only the velocity, we can figure out both of those things by using that time data as well. So the change in like distance traveled over change in time is going to be velocity, or the change in distance is velocity times change in time. Similarly, for acceleration, we can take the slope and look at change in velocity over change in time gives us acceleration. And so that will let us answer some of these questions here, like which car traveled further after 10 seconds, A or B? Well, we can look at 10 seconds. The car A has this sort of triangle shape. So if we can calculate the area under that, the area of a triangle, then we'll know how far it's gone. And so I'll just sort of put a little calculation over here for car A. The area of a triangle is 1/2 times the base, which is 10 seconds, times the height, which is 45. And car B, we have a triangle in the beginning. So 1/2 equals 1/2 times 5 times, what's the height there, 35, plus the other 5 seconds are a rectangle. So 35, same height, times 5. And that's how far car B has traveled. And so I can go ahead and say car B went further. Great, did it. Which car had the fastest acceleration or deceleration at any point during the race, A or B? Well, the acceleration and deceleration is the slope. And so what's the steepest slope on this graph? Maybe I can just look at it and tell visually, like it's definitely not these flat lines or this sort of like sloping in the middle here. It's probably either at the beginning or the end. That's where they're really steep. And these end ones look about the same, and maybe about the same as car A here, but that first bit of car B looks like a really, that's the steepest one. That's the highest acceleration. So I'm going to go ahead and say it's car B. And that's right. And you could calculate it to double check, but this is how car B managed to travel further than car A, even though it never hit as high of a velocity in those 10 seconds. It did accelerate faster in the beginning. And so you could take this information and get, which one went the furthest overall and calculate the area under the entire figure for both. And how far did car A go? Again, just calculating the area under the curve. I'm not going to do that here, but you know how to do that. It's the area under the curve gives you the distance.